With new video for the calculation of the electric field because of the uniform charge distribution of the spherical cell. We have this spherical cell of radius r carrying surface charge constant uniform surface charge sigma naught at a distance r from the origin or the centralized at origin. Now we have to calculate the electric field at any point on the z-axis. This point, let's say it is at a d distance far away from the center. We'll do this problem. Then if time favors, we will move to the next problem where the surface charge density is not uniform, but the surface charge density depends on the angle theta and phi. So we'll do these two problems in this video if time favors. Otherwise I'll make the next video for this one. So uh, in this problem we are not going to use Gauss law. Gauss law would be easier to find the electric field at that point exactly, but we are not going to use Gauss law. We are using the fundamentals law to calculate the electric field. Okay, so uh, the fundamental, I mean the electric field, because of we calculate the electric field because of the small charge element in the surface. Then we integrate over the whole surface and calculate the electric field, unlike considering some the Gaussian surface and calculating the field from that, in case of the Gaussian law, in case of the Gauss divergence theorem. So yeah, so let's move ahead. uh, let me draw a sphere here. Oh, I'm sorry, I'm not pretty good on drawing. Okay. I will do something. Oh, this is my z-axis, this is my x-axis, this is my y-axis, and I draw a sphere here. I have a sphere and this distance is r, this distance is r. Okay, so I am going to consider a surface element here, which is okay, just let me remove this. I'm going to consider a surface element here. Okay, so this distance is this is the surface element. This distance, as you know, uh, let us say this angle is d phi. Okay, sorry, this is d theta. Let me erase this. If I draw something like if I look on the azimuthal, sorry, the angle, it is like this. Projection on the, let's say this is x, y and z axis. Projection on this is my phi, right? So the its projection on this is d phi. Let me write this as d phi, this angle, small angle, and this angle is theta, and let me say this angle is d theta, right? So yeah, I have just two variables since this is the r, this total is r, and it carries the surface charge sigma naught. So I first of all calculate the charge on this small surface element. This a small element is subtending theta angles, d theta angles at the origin along these vertical directions, and subtending d phi angle along this azimuthal directions. So yeah, so I'm going to find first of all the charge enclosed or the charge carried by this part. This is dq. How do I calculate dq? Is the charge in that small area element, the area, sorry, the this charge can be calculated as the surface charge density of the region of the sphere. So this is the surface charge in a area dA. dA is the small area element, so which can be written as sigma naught in a spherical coordinate in the spherical cell. This area, if you look on, is this length into this breadth. So it would be something like this. It would be like this. It is d theta, it is r, and if we look from azimuthal part, right, if we look from this angle, suppose this is the oh, sorry, I'm not good on drawing, so maybe I need to work out a little more on. Suppose this is my vertical axis and this is the origin, and this angle gives me, suppose I have this is x-axis and new, this is y-axis, let me say this is y, this is x, and this is, let's say, this is g-axis. Then this separation gives me, if you look on here, exactly same like if I look on this angle and this angle is exactly same, which I have considered here is this is phi and this angle is d phi. So if this is d phi and this is r, this can be written as, how can I write that, is like r sine theta. If you look on that, this is the d theta, this is the straight line, right? If you write the first of all something like this, I am not much good on drawing. Okay, so this is for understanding only, otherwise you could directly, I am doing some calculations how to perform the small area calculation in the spherical coordinates. So if I draw a perpendicular here, okay, this one here, then this distance would be then this line would be r sine theta into d phi. It means if you go here, it would be different. If you go here, it would be different. It would go here, it would be different, and that depends on the theta, right? So this depends on the theta. And next, if you look on this part, it would be r into d theta. R is constant. It would be r into d theta, right? So I'm going to calculate the area of that region. This area now is the area of this small rectangle, which is r d theta into r sine theta into d phi, which gives me r square sine theta d theta into d phi. This is my area element. So the small charge enclosed on that surface is sigma naught r square sine theta into d phi. If we want area or the total charge on the whole spherical surface, we integrate over the theta from 0 to 180 degree and d phi from um, 0 to 2 pi degree. So this is the way. we perform. Now we have the small charge element. Now we calculate the electric field at point D from the origin because of this charge element, right? We perform this electric field. So let me make a bit clear on this by removing this thing here. Okay, so I remove this as well so that I can draw clear figure here. Okay, so I have sorry, I am going to it would be useful to draw it here. Okay, so this is the point where the distance from origin is D, and we want to find the electric field because of the this surface charge. Our electric field is something like this on the direction away from the origin. So sorry, the away from the point charge. It is on that direction, but it has components, many components. It has vertical components, horizontal component, and next horizontal component on the inside the paper. So we are interested, finally we are interested only on the Z component, because we are going to find the electric field along this line or at point D, and the other components because of the uniform charge distribution and the spherical symmetry. I have explained what is symmetry and how it cancels in case of the circular loop in the previous video. You can check that for more details. It get cancelled and only this will survive, G component of the electric field, because of the sphere is survived in total. This small element could have three components, but if we take the whole sphere, because of the spherical symmetry, the electric field of this element and the element just opposite to this gets cancel out in the horizontal directions, and the electric field adds up in the vertical direction. So the only G component of the electric field will survive. So I'll be looking only on the G component. But so let's move forward with the same electric field because of the small element, which is K d cube uh, r vector of the point P. This is the point P, let us say, minus position vector of the point source point divided by rp minus rs whole cube. So we move from this one. So let's calculate rp. Rp is what? Rp and rq. Rp is the position vector of the point this, which is sorry, the d dot k, which is 2, and rq is the position vector of this point, the small element. It is exaggerated, actually this is a very small element, which in the spherical coordinate can be written as r sine theta cos phi along I direction. Here is r is capital R, and r sine theta sine phi plus r cos theta k. So the difference of these two, rp minus rs, goes like minus r sine theta cos phi I minus r sine theta sine phi j plus d minus r cos theta k. And if I take modulus or the magnitude of this vector, it would give me r square sin square theta cos square phi plus r square sin square theta sin square phi plus d minus r cos theta whole square. If you do simple algebra here, you will end up with the result uh, r square sin square theta plus d minus r cos theta whole square. Here the algebra is like I'm just taking sin square theta, r square sin square theta common, then it would be r cos square phi uh, plus sin square phi gives. So my electric field expression, this expression on number 1 becomes dE vector equal to k dq we have calculated over here is sigma naught r square sin theta d theta d phi, sigma naught r square sin theta d phi into this rp minus rs. From the expression rp minus rs is this expression. So I write here inside the bracket minus r sin theta cos phi I minus r sin theta sin phi g plus d minus r cos theta k over by root under r square sin square theta plus d minus r cos theta square to the power 3. This is the electric field because of the small charge carrying element, surface element dq. As I said, this is very small element, almost a rectangle. So now to calculate the electric field at point D, we integrate all over the surface because of the all surface charges. So R is fixed, so we integrate over the surface. Now I have three components: I component, G component, and the K component. In case of sphere, because of the spherical symmetry, it is symmetry about the axis. So the x-axis and the y-axis, this is x and this is y, the x-axis and y-axis, their overall contribution is 0 because of the symmetry. So I can take only the G component here. So x and y components drop to 0 because of spherical symmetry. Because of net, let's say net x and y components drop to 0 because of spherical symmetry. So I take only the G component, right? So the G component over the surface, so it becomes k sigma naught r square sin theta d minus r cos theta into d theta d phi over by r square sin square theta plus d minus cos theta square to the power 3 by 2. Now I calculate this integration. I take out the constant terms out of the integral sign. Sigma naught is constant r square. So I have here 0 to 2 pi into d phi 0 to pi, this is over the theta, d theta, d minus r cos theta into d theta, right, over by r square sin square theta plus d minus cos theta square to the power 3 by 2. This goes like this is integration over the surface in the d phi, so integration over this is how much, this is 2 pi, so 2 pi k sigma naught r square, and this integration I take this, sorry, this integration, this from 0 to, let's say, 0 to this term, and this is this whole to the power 3 by 2, right, 0 to pi 3 by 2. So what can I do right now here is I calculate the integration of this. The integration of this term is if you do simple algebra, you will end up with, I'm not going to do the overall calculation here, you have to write yourself. I'm just going to write this. If you look here, this is, let's say this is x, right, this term and this term are the same, and this term is the uh, yeah, so we have sine theta also here. Maybe I forgot to write here is 1 sine theta. Let me make sure this sine theta into d theta. So yes, there is no d theta, I have already written here. Into sine theta. So yeah, so the integration becomes, because of this, d minus r cos theta divided by r minus d cos theta divided by d square root under, if we just square it and open this becomes, here is r cos theta, okay, we're getting r from this r square cos square theta, r square sin square theta gives r square, right, and plus this d square minus one term from here, 2rd cos theta, this theta by 3 uh, goes up, minus 3 by 2, and in integration power get added, so it becomes only the 1 by 2 minus 1 by 2, and it again goes down, it comes something like this. And the integration run from 0 to pi, which goes like, I will write it here, 2 pi k sigma naught r square. If I write pi here, cos pi is minus 1, so it becomes r plus d divided by d square. If I write cos theta, cos pi, it is minus 1 minus plus 1, a square plus 2ab plus b square is the formula of a plus b whole square. So I write r plus d here minus uh, now the cos 0 is my 1, so this becomes d minus r over by a root under, if this is 1 this becomes minus r minus d whole square. Alright, r minus d, or mm, I'm sorry, where I am doing mistake, r plus d or d minus r, I am doing here the small mistake. This is d minus r, okay, d minus r, and in our case d is greater than r. D, since it lies out of the surface, the point lies out of the surface, so it is this, or let me just replace it by this part. Okay, d is greater than r for the point outside, for the point outside this sphere. So our electric field becomes 2 pi k sigma naught r square. This I can just cancel 1 by d square plus r minus d by d square r minus d. I can just cancel this out. That gives me the d square and d square, and it end up with 2 by d square. So 4 pi k 4 pi this r square, 4 pi r square is the area of sphere into sigma naught total charge enclosed by the sphere k by d square. If you look this very carefully, it is equivalent to the electric field along z direction. Electric field due to the charge q equals to 4 pi r square epsilon naught. Here 4 pi r square is the area of sphere multiplied by the charge density, surface charge density. This gives me the total charge on the surface. So the electric field, because of the uniform charge distribution of the sphere, is equals to the electric field because of the point charge. This is the electric field because of the point charge lies at the kept at the origin, or in other words, what I would say is the exactly same electric field we could get if we put the point charge here, which has the magnitude q equals to 4 pi r square epsilon naught, and find the electric field at the point d. It will be upward. This time the electric field because of this point charge lies at the origin is exactly same as the electric field because of the sphere carrying the sphere of radius r carrying the same charge 4 pi r square sigma naught, or in other words, the electric field because of the point charge 4 pi r square sigma naught at the origin, uh, electric field at point d because of the point charge lies at the origin is exactly equal to the electric field because of the sphere carrying the surface charge sigma naught. This is very important conclusion of this problem, and it could be frequently used uh, in later discussion. So it is actually because of the point charge. So what conclusion we can draw from here is the electric field because of the point charge can be approximated by the electric field of the electric field of the spherical charge distribution, which carries the charge density sigma naught, and whose center is exactly in the position of the point charge. So yeah, uh, maybe the second question of this set, problem number B, we will discuss in the next video because we are already crossing the time boundary. Okay, see you in the next video.